All right, so where we left off was I started talking about functions, but then I went off on a few tangents. Um, First, talking about the meaning of the number that's printed at the side in square brackets whenever you have output. Um, and just clarifying that that number gives you the index of the number that's printed on screen right next to it. The next little thing I want to talk about before I really talk about functions is, again, continuing with this idea that we have the C function, which creates, which allows us to store objects, so for example, named A, whose contents have multiple values, not just a single numeric value. How does all the tools we've learned so far how do they work when you've got not a single value but multiple values? So we've talked about math. So this example here, we create this vector object, and I click run, and I say A times 2, what's going to happen? Well, what's going to happen is that for every element of A, R is going to go in and multiply it by 2. So run that, and we get 2 is 2 times 1, 64 is 2 times 32, 468 is 2 times 234, and 18 is 2 times 9. Similarly, if we have two vectors, so vector A is 1, 2, 3, 4, vector B is 2, 4, 6, 8, and we try to do math on them, so for example, A plus B, how is it going to work? Well, the way R does things is when it has two vectors that are the same length, it will multiply them element-wise. So the first, or it will do the whatever operation you have there element-wise. So here we've got addition, so what it's going to do is going to look at element 1 in A and add that to element 2 in B. And then it's going to look at element 1 in A, it's going to add that to element 1 in B. Element 2 in A, it's going to add that to element 2 in B, and so on, yielding 1 plus 2 is 3, 2 plus 4 is 6, 3, 6, 9, 4, 8, 12. If you have unevenly sized vectors that you try to do math on, so I'll add this in here, so tangent 5, 2, 3, 6. Well, maybe I'll actually, if you have unevenly sized vectors, but one is a multiple of the other, what R will do is it will say the first element A plus the first element in B, second element in A plus the second element in B. We've got no more B left, but we have some more A, so it's just going to repeat back over. It's going to loop back over what B was. So now it's going to have the third element of B plus the third element of A plus the first element of B, and then the fourth element of A plus the second element of B. So just to show that, 1 plus 2 is 3, 2 plus 4 is 6. It's run out of B, so it's going to go back to the beginning of B. 3 plus 2 is 5. 4 plus 4 is 8. Now, that's two vectors with uneven numbers, but one vector's length is a multiple of the other vector. Let's try when one vector's length is not a multiple. So we've got 3 in one and 4 in the other. Well, what happens is the same behavior as I described above with uneven elements. It cycles back through B, but you also get a warning message saying that one object is not a multiple of the other. So again, 1 plus 2 is 3, 2 plus 4, 6, 3 plus 3, 6, 4 plus 2, so we go back to, we've run out of B elements, we've got one last A element to deal with, so it cycles back to the beginning of B and adds 4 with 2 to get 6. So if you ever see that message, it means that you've got two vectors that you're trying to do math on, and they're of uneven lengths, and one just can't be, one isn't a multiple of the other. All right, so back to functions. So We're pretty familiar now with the C function. The C function merely takes a bunch of values and puts them together so that when we do math and other things, we can do math in a vectorized way. That is, the math is applied in an element-wise way. Now, let's take a look at another function that's built in. So another function that's built in is the mean function. So here we're saying I'm going to call the function called mean, and as its argument, I'm going to pass the value a, or I'm going to pass the object a. So what that does, mean will expand a and see that the value of a has a vector of numbers, and it will compute the mean of that vector of numbers. Now, I didn't actually have to create a first and then pass in all those values. I could have just nested the call to the two different functions. We've got the C function and the mean function. I could have said the C function, concatenate these all into a vector, and then outside of that, take the mean of all that. So that's nesting of functions. So if I run that, we get the exact same result. So it depends on the scenario whether you create an object and then run a function on that object, or you create the objects, or if you start nesting your functions. It depends on the context whether one's easier or less typing than the other. A very useful function that you'll become very familiar with is the read.table function. Now, so far the functions we've seen have taken arguments, but those arguments we've just been passing values as those arguments. Next, we've got arguments, but those arguments have this weird structure. So I've got, so to walk through this line, we're going to create an object called A. So if A already exists, we're going to erase it, create an empty object called A. And inside A, we're going to put whatever's on the right-hand side of the equal sign. So what's on the right-hand side of the equal sign is a function. But we're passing arguments to that function, so the function is going to do some computations on, that are dependent on those arguments, and will return a result that is then stored into A. So when you're reading data in from a file, it's probably pretty intuitive that one of the arguments is going to be the file name. What file do you want to read data from? So there happens to be an argument to read.table whose name is file. And here, when I'm calling the function, I'm passing as the named argument file the string mytext.txt. So if we go out to the files browser here, I'm just going to make it big. You'll notice that I've actually put in a file of that name in your file browser since the break. So there is a file there called myfile.txt. There's another argument where it's header equals true. I'll go into these in just a moment. And there's another argument, sep equals this other thing. And I'll explain these arguments in a moment, but the critical thing here is that in example 4, I have a function and lots of arguments separated by commas. The arguments have names, and I have it all on one line though. So if I run that, it will read in it will create this new object called A, whose contents, we get a little summary here. It says 12,800 observations of 10 variables. So it's a table of variables representing the data from whatever was in that file. I can click on that, and it will bring up a little data editor down here, so I can see what it actually read in. So I can see that it's, I guess, data from a reaction time study where I've got lots of trials within lots of subjects, and various columns tell me different things about what conditions the participants experienced during the experiment, and I have many different subjects. So lots of columns here. So that's what's being stored in A as a result of running this call to read.table. As I said, I'll go through read.table in more detail, what each of these arguments mean, how I know that there's arguments or what they are. But the critical thing that I want to point out is that you can have a function with named arguments separated by commas, but all on one line. But it's really hard to read. It's hard to sort of parse what's going on inside this function. What's nicer to read is this format. So it turns out that R ignores white space. White space, well, for the most part, ignores white space. I already told you about the scenario when you have two equal signs, you can't have a piece of white space in the middle. It doesn't like that. But in most other cases, R ignores white space. So white spaces are literally the space bar, hitting the enter button or return button, or hitting the tab button. So here what I've done is I started typing this. I typed a equals read.table, but then I immediately hit return. And furthermore, I then, on each line, I've hit tab. And then each line, each argument that I want to pass to read.table is separated by another new line. So what this achieves is that it makes it nice and visually clear that this is a call to a function, and that all these things are sort of things to do with the function. They're all arguments being passed to the function. So another nice thing about another feature that is important is that I put the commas at the beginning of the lines, of the new lines. I used to, a lot of the time, have everything just like this, where I'd have the commas at the end of the line. But it's really easy to, if you start adding other arguments and things like that, it's really easy to forget to put a comma, and it's really hard to see that you've forgotten to put a comma. If you get yourself used to putting commas at the beginning of the lines, because, again, R ignores white space, but it wants the arguments to be separated by commas, it's really easy to see if you've forgotten a comma. So, for example, there, that just visually, that step really stands out. So I would be able to see, oh, I forgot to put a comma in between the header argument and the sep argument. So don't get too caught up on what each of these arguments mean. The general idea, though, is that functions take arguments. They can be named arguments. So I happen to know that the read.table has, of many arguments, there are 3 of them whose names are file, header, and sep. But arguments need to be separated by commas. And when I'm doing something where I have multiple arguments to a file, I like to separate them across multiple lines, putting the commas at the beginning of the lines and tabbing everything in by one tab, just to sort of have a nice visual hierarchy of the function. So I talked about these as these lines that we have here as named arguments. So I've got read.table as a function. I happen to know that one of its arguments is file. So what I'm doing by saying file equals my file is saying that when R runs the function read.table, it will, whenever it needs to look for a file, it will, or whenever it needs to do any computation on internally its object called file, it will actually look for whatever value I put to the right-hand side of the assignment variable within this call to the function. So our read.table has a large number of named arguments. Whenever you have a function that has named arguments, you don't have to specify the name, as I've done here when I'm calling it in example 5. And indeed, example 5 is exactly the same as example 6. So, or at least it will yield the same results as example 6. So if I run that, I'm still going to get A as being, it will delete A, but then create it again and read in the data, and it'll be the exact same data as we had in before. So the difference between these two is that in example 5, I actually provided I explicitly said, okay, the named argument file is equal to this, the named argument header is equal to this, the named argument sep is equal to this. Here, I just assumed that R would know what arguments I wanted to pass each of these values to. And it worked. Only because it happens that in the various named arguments that read.table is interested in, it just so happens that file, header, and sep are the first three arguments that it expects. Unfortunately, this won't work all the time. So if I just forget what the order of the read.table arguments are, I can still use read.table accurately if I always provide the name of the argument that I want to assign to. So here, example 7 should run exactly the same as example 6 and exactly the same as example 5. Indeed, it's got all the same information in example 5. I've just moved around the lines. So now sep is being provided as the first argument, header is provided as the second argument, and file is provided as the third argument. But because I've named each of the arguments, it knows that what each of these values is intending to, what role each of these arguments is intending to play as. So when I run that, it just runs fine. However, if I fail to provide the names to the arguments, and I provide the arguments in an order that, or provide the values in an order that isn't what the default ordering is, it will usually not work the way you think it's going to work. So I get an error in this circumstance. So the big point here is that whenever you've got a function with named arguments, while you can just omit the names when you're calling that function, it's always a good idea to put the names in, particularly with complicated functions like read.table that has something like 60 different arguments that you can supply to it. So we'll get into read.table a little bit more later. I guess, one thing that, how do I know read.table has all these arguments? Well, we can look at the help. Let's bring up the help. And I'm just going to say read. Oh, so as soon as I start typing, it's going to give me some things that I think that I might be interested in. Indeed, read.table is in there. So I can click that. And is it searching or what's going on? Usually there's, I think I may have to actually click it and hit enter. There we go. Yeah. Click it and hit enter. I'm going to hide the console, maximize the help window by clicking the button up there, and searching for read.table will give me a help document. The help documents are all similarly structured. They have a bunch of sort of header information. Okay, let's see. Stay on page. Okay, I think my browser interpreted my swipe as a go back, which is not what I wanted, but it's back to where I wanted it. So there's some header information here. This is saying that the help documentation is for the function read.table, which is in the utils package. You don't need to worry too much about that, and that this page is a piece of our documentation. Here's a title associated with read.tables describing sort of general use, and a little paragraph, sentence or so, description of what read.table is used for. Reads in a file in a table format and creates a data frame from it with cases corresponding to lines and variables to fields in the file. So the usage area shows sort of an example usage of read.table without actually, it shows that the order and the default values for a bunch of the arguments. So the first argument to read.table, as we know, is going to be a named argument called file. So it's expecting you to provide it a string value that corresponds to the file that you want to read in. Next argument is header. We don't know what that means yet. Next argument is sep. We don't know what that means yet. So all of these, it's showing you what the order of all the arguments are and what maybe their default values are. So if you fail to supply a value for that named argument, it will just revert to its default value. So here, header has a default value of false, whatever that means. Sep has a default value of 2 quotation marks, so that just means any white space. And then there's a whole bunch of other arguments, some with default values, some without. So how do I know what each of these arguments do? Well, that's a little bit lower down. So this particular piece of help documentation shows you things about read.table. There's also some variants of read.table that are that are related. So there's read.csv as a function. But because they all share similar structure and arguments, they all just appear on one single help page. But down here nicely, below the usage section, we have an argument section. This argument section describes the purpose of each of the arguments, of each of the named arguments. So file, for example, is telling the name of the file from which the data are to be read. So it gives a little description on how to find files and things like that. Here's header. We didn't know what header, or hadn't described what header was. Header, a logical value indicating whether the file contains the names of the variables as its first lines. So do you have a header row in your data file that tells you the names of the columns that you're going to be reading in? The default value is that false. So if you fail to provide a header, if you just provide a file and that's it, it will assume that the first row of data, first line of information in your file is data, and will just make up column names for those columns. But if you set it explicitly to false, as we do in our example, let me pull it up here. So, if you explicitly set it to true, as we've done in examples 4, 5, 6, 7, it will look at that first line, treat all the information that it finds in that first line as names for columns that are then going to start with data in the second line. So that's typically the way I create all my data files from my experiments. Usually I have something at the head of the in the first line of the data file saying what each of the columns' names are. So that's a pretty common argument to specify as true. Sep is another one that we were using before, the field separator character. So presumably your data is written out in rows and columns, but how do we know when one column turns into another column? This is what the sep character says. The default value is just any white space, so that can be kind of troublesome if you've got, say for example, you've got stimuli that are sentences, and in your data file you have one column that just lists the stimulus, so it's a sentence. You're obviously going to have spaces in your sentences, so you might want to have your data files set up with an explicit, unique column separator, for example, a tab character. If you want to have a tab character, that's what this weird /t is about. So it's in the /t is inside quotation marks, so we know it's a string, and it just is a standard that /t means tab. So if I actually go out and I look at my data, so I can actually open up files. Let's see. I'm going to try refreshing. Click files, there we go. So if I go in my file browser, I click that myfile.txt. It's kind of big, not super big. It's almost a megabyte. It's saying, giving me a warning with big files. It may take a little bit of time to open it. I'm going to say yes. So it opens it just like a text file. And I actually can see that there are tab characters separating these different columns. So that's why I specified /t as the separator here, because I would have created this file, or I would have programmed my experiment to generate data files whose columns are separated by tab characters. Let's see. So back to that help document. So you can see, we'll go through some of the ways to customize the read.table function to read in all sorts of wonky data file types. I wanted to use this as the example of how to look up a function. So you can go to the help documentation, type in the name of the function, and then you hit enter and it brings up the documentation. How to parse that documentation, you can look at the usage, you see all the named arguments and what their default values are. And then down here in the arguments, you can get a description of what those arguments' role is. There's also way below, so there's a lot of arguments to read.table, meaning that you can tweak read.table to automatically read in nice, very weird data formats if you need to. The defaults for read.table are usually pretty good. There's a details section, which usually, depending on the function, has different content. Usually it tells you about what it's going to try to do in a little bit more detail than the couple sentence description that it had at the top. There's usually also a value section, which tells you what to expect as the result. So here it's going to be a data frame. So read.table takes the file as input, and we'll have a data frame as output. A data frame is a type of object that can be stored in memory that has rows and columns. It's a little bit more complicated than, there's also a matrix object that we're not going to deal with really. A matrix object has rows and columns, but a data frame has rows and columns where the different columns can be different data types. So one column might be all numbers, another column might be all strings, another column might be all logical values, another column might be something we haven't talked about yet, but something called a factor. So a data frame has the ability to have different types of data, which is exactly what we usually encounter when we have data from experiments. There's also usually some minor notes that you don't really need to pay too much attention to. If you're looking at the help documentation for a function that implements some novel or statistical procedure, there might be reference to where it was originally published. There's also sort of a see also section where it links to other functions that are related to the function that you're looking up documentation for. And then there's usually an example section where there's examples of using that function in different contexts. Read.table examples aren't super useful. We'll do a lot more examples in the afternoon sessions. So just to get help on read.table, one way is to click help and type read.table in there. For those that don't like the point and click so much, let's see. You can, just in the console, if you type $read.table, it will bring up the documentation for read.table. If I didn't know about the read.table function, how would I learn about it? Well, I can do a keyword search of all the R documentation. And to do a keyword search, maybe I think, okay, I want to read in data, so maybe I'll look for the word read. To do a keyword search, you do $read from the console, and it will give me some search results in the help tab. So it'll read through. Eventually, we'll probably find things. You'd want to look at each of the descriptions to see which one sort of suits what you're actually interested in. But eventually, read.table is down here somewhere. Yeah, just the very last one. You can also do, excuse me. Keyword search, again, up here. If I just type read, sorry, this will only let you search for functions. It's, there we go. It's this. So when I bring up the R help, let's see. Bring up the R help one. If I just type read here, it will do. Oh, I think this is just, let's see. Gotcha. So I believe that this will search the current page that's loaded. But if you click the little down arrow, oh no, that's just history. Okay. Well, I guess the only way to do keyword search is by the double question mark. I feel like I remember seeing another way to a way to do keyword search from within the help tab. I'm clearly not seeing it though. Help. Sorry? Right. Yeah, maybe that's what I remember seeing. Yeah. So to show you there's the main R help page, which you can get to by clicking this little home thing. And then if you scroll down just a little bit, there's the search engine and keywords. And you can, if I type read in there, let's say search, it will give me that same search page as I got from just typing question mark, read. So it's kind of helpful. If I know the name of a function, I can look it up. If I have a keyword that is associated with the function, I can try my luck at actually looking it up through the keyword search. But another way to, I guess, get started with R and sort of increase your vocabulary of functions that you know are in R is to use a nice little, use some of the help documentation that are provided online for R. So I'm going to open up just a new window here and go to CRAN. So the website for R, cran.rproject.org. And this is where we originally downloaded R, but there's also a bunch of stuff on the sides in addition to the downloads. So documentation, that seems useful. There's the manual section, so I can click that. Don't read any of these. They're not going to be useful for you. They're very technical. There's FAQs, which are useful. They're more on general usage. There's a general FAQ. There's a platform-specific FAQs. Might be useful to take a look at those. I haven't looked at them in a while, so I can't recall how particularly useful they are. But frequently asked questions tend to be a little less technical. But the documentation that I highly suggest you take a look at is in the contributed documentation. So contributed documentation starts out English, but there's obviously other languages that things have been translated into. Let's see, lots in French there. The English starts out with a section called documents with more than 100 pages, which implies that there's another section, documents less than 100 pages. So we'll scroll down, see documents with fewer than 100 pages. And within those documents, there's a number of, actually, there's even short documents and reference cards. This is a good place to start because there's a couple good just reference cards. I like this one. So if I open up the PDF, I actually want to download it and open it up explicitly. Save linked file. Oh, exactly. Go open that. There we go. So this is a reference card. It's meant to be printed out and kept by your desk whenever you're working. The nice thing about this reference card is that it organizes the different functions in terms of, it lists a whole bunch of functions, but it organizes them in terms of the I guess, domain of usage. So getting help, there's a whole bunch of functions that it lists that are associated with getting help on things. Input and output, it lists a whole bunch of functions that are useful for doing that. Read.table is one of them, but there's a bunch of other related functions. Creating data, so we've got C in there, so we knew that C allows us to create a vector out of a whole bunch of elements that we specify. Here's that example of using a colon as a way to create data, to create a sequence of data. Apparently there's a sequence function that does the same thing as using the colon. There's a bunch of other functions that are useful for creating data. Slicing and extracting data, so we'll be talking about this probably in the afternoon, about once you read data in, say, a data file, how do you get R to talk about just a single column or a single row or a single cell in the column and the rows? If you need to find out, so for example, which row has the maximum reaction time, there's some functions here, for example, which max in the data selection and manipulation. It gives you a bunch of the math functions that are useful: sine, range, sum, diff, product. Functions for manipulating strings, so searching for, say, all your stimuli or sentences, and you want to select all those sentences that have the word cat in it. String functions will be helpful for that sort of thing. Matrices you're probably not going to be working too much with. The advanced data processing, we've got better ways of doing that. Reshape might be useful. Plotting, I'm going to give you some better plotting tools than default plotting functions. So really, actually, the whole third page is probably not very useful. And you've got some statistics here. So you've got ANOVA, AOV, binomial test, pairwise test, t-test. Those might be useful. I'll be showing you how to use ANOVA in a very user-friendly way. So really, I guess the first 2 pages would probably be the most useful for you, just beginning off. You can feel free to take a look, though, at some of the other reference cards that are provided by other people. There's also a number of other contributed documents. So these are generally documents written by just people that provide them for free online, just to help others learn R. There's a number of good and amusingly named, a guide for the unwilling S user. S is a paid version of R that existed slightly before R, and folks decided that they wanted to take the S language and make it free and open source and better, so they created R. So a lot of code that's written in S will work for R and vice versa. So a guide for the unwilling S user, or R user, that's useful. A friendly beginner's R course. Yeah, so there's a number of good ones in there. There's also much larger ones. So practical regression in ANOVA using R. It's Fairway's book, apparently is pretty good. I haven't actually read it all myself. So some of the larger ones will be for more, so bioinformatics, data mining, more niche scenarios. So yes, for help on functions, you want to look at the reference cards. For general documentation, there's some good documents there. I'm, of course, going to be recording these and posting them online. I'm hopefully going to be generating a document of my own that summarizes the content of this workshop. So you'll have a number of tools at your disposal for learning R. Now, So far, I've just been talking about the built-in functions. The built-in functions are generally functions that the creators of R have decided are so useful that they should be available to all users immediately. There's a number of additional functions that other people have written that haven't, I guess, achieved the status of universal recognition of being applicable across all domains. So, for example, maybe I'm interested in spike train analysis of single-cell unit recordings. Somebody has written a package that is dedicated to the analysis of that sort of data. I don't want to redo all that person's work in terms of research on how to properly analyze that sort of data. I'd rather just reuse their code. So I can go fetch code that they have provided for free online, hosted by the folks that make R. So an example is if I'm dealing with data that's circular in nature, so I don't know, you have data where you're looking to say discus throwers and looking to see how far and what angle they throw things as a function of some experimental manipulation. What you fundamentally have is circular data where you've got angles and magnitudes, so you probably want to use circular statistics. So there's a package called circstats that maybe I want to use. Circstats doesn't come pre-installed, at least as of a while ago. It might have become one of the base packages, but last time I checked, circstats doesn't come pre-installed, so I have to install it. What's nice about R is that you don't have to go to the web and download something and then run an installer. You just can run a line of code, and R will handle going to the web, downloading, and installing. You can do this by a command at the command line, or, if I recall correctly, you can use the Packages tab. So up here, there's the Packages tab, and there's an Install Packages button. So let's actually just try going through the process this way. So install from, and you can choose your repository, that is, what website is it going to try to look for. There's the CRAN website. CRAN, again, is the folks that develop R. So they have their own server where they store all the packages people provide, and that's most of the time how you're going to do things. There's also the ability to install a package from a local file that somebody's just given you. That's going to be a rare scenario. So the next thing is, what packages do you want to install? So I want to install circ, and it happily gives me some suggestions based on its knowledge of what's on the CRAN server. So circstats, install to library, keep whatever default they give you there, and install dependencies should probably be kept checked because packages usually rely on other packages. So if you don't have those other packages installed, even if you install this package, it won't work because it will need other things to be installed as well. So checking install packages will go through the network of dependencies and make sure that every package has every other package that it needs installed so that everything will work. So if I click install, it will do a bunch of stuff in the console. It will basically, this part just saying it's downloading, and it downloaded really quickly because it was a really small file, and then it's doing some installing, and then it just says, I'm all done. This message here you can ignore. It's just saying where it downloaded the file as a temporary location, but you can ignore that. So now that it's installed, again up in this package area, I can see that, now I've got circstats as a package that's available to use. Now, I've installed it, but anytime R starts up, it only starts up looking at the packages that are in the base install of R, the built-in functions. So if I want R to load the, library of functions that are provided by the circstats package, I need to, I need to do something to tell R to load that library of functions in. So I can either do it from the command line again by typing library and then in quotation marks the name of the package that I want. Or, again, I can just go to this Packages tab and check the circstats thing. Circstats depends on mass and boot. So when I checked that, it automatically loaded up both mass and boot. I'd probably recommend that you always put your, that you not use the point-and-click interface for loading up libraries. It's okay to do it for installing libraries because you're only ever going to do that once. But for loading up libraries, loading up the library of functions that a package has, I'd use the library command in your code. That way, when you go to run your code, or say you share your code with somebody else, they know that they need to install the circstats package before they're able to run the code. And it's explicit that in your code, the code loads the library. That way, you don't have to point and click and do it every single time. So, yeah. So there's a ton of contributed functions. How do I know what functions are out there? So I'm going to go back to CRAN. And in the software area of the left-hand side menu, there's a packages section. If I click that packages section, it tells me there's 4,000 available packages. So you can just list all the packages that are available by date of publication or by name. Let's just take a look at it by name. So if I do it by name, I can see that there's a lot of packages. I think they'll all be on the same page. Yep. But there's 4,000 of them. Each one will list its name with a link and then just a little short title for it. So ABC, I'll click that, and it brings me to the page for the ABC package, which gives a little description, when it was published or last updated, what other packages it depends on, who the authors are, how to contact the authors. Sometimes there's a web page that the authors have developed that have some instructions or tutorials that will be listed on the package information page. There's some downloads that you can get, but you really don't need to bother with these downloads because the downloads are for if, for some reason, installing the package from R fails for some reason. Usually you won't bother with it. But, I don't know, looking through this big list of packages is rather daunting. So what's nice is that there's actually this other feature of the CRAN website called Task Views. So I'm going to click Task Views. And Task Views is a section of CRAN where it tries to separate the packages and their descriptions into different, general data analysis tasks. So if you're interested in Bayesian inference, you'd go to the Bayesian task view, and you get a page that talks about what packages are available for Bayesian inference, and specifically goes through different domains of Bayesian inference, the packages available, and a brief description of each one. Let's see, something else that would be interesting for us. Psychometrics. So there's a psychometrics task view that lists a whole bunch of psychometric-related tasks. There's also, I guess, a social sciences task view, which might be useful. Certainly linear general linear models are things that we use in social sciences a lot. So the task views are very useful for just getting a sense as to what packages have been provided by others. Another way of just searching for packages that are useful is, let's see, Who should I go to first? There's the search. I find the search that's associated with the CRAN website not as good as another website. The search for the other website is rseek, r-seek.org. Oh, no, there's no dash. And this, so let's see, maybe I want to look at generalized additive models. rseek will bring up a whole bunch of results. It's hard to see because my screen is only 800 by 600, but usually these panes, this left side of the screen and the right side of the screen are a little bit more equally sized. But the left side of the screen just gives a bunch of raw results from the web, but the right side of the screen has a whole bunch of tabs. And we've got, you can look through functions to look at generalized additive modeling. Here, there's something that seems to be appropriate. So one of the first hits is using LME4 to fit generalized additive mixed models. That might be useful. So there's, this will search all the package descriptions for things. You could, of course, just go to the package descriptions list, which is here, and search for one of the words, which might take a while because it's a long page. Hey, yes, spelling it correctly. So if you look for generalized additive, you might find some appropriate things that way as well. There's a, finally, with regards to contributed packages, finding ones that are good, there's a site called Crantastic. Crantastic.org. No, not Citic. And it's kind of like a, it's a site that lists all the packages, but also sort of lists them by popularity, user-rated popularity. Let's see. If we want to look at packages and list them by popularity, there's a way to do that somehow. Well, you can also search all the packages on this site. There used to be a way people can provide reviews of packages on this. You can provide tags with packages and use a nice tag cloud. So I really like Crantastic. It's fun to just look up the ratings of the different packages. Or if you see two packages that have similar functions, maybe you want to look up the ratings, and maybe one is better than the other as rated by other users. So Crantastic is a good page to use. So, so the last little bit that I think we'll manage to get in the context of the morning session is the third set of functions that you can do. So you can use the built-in functions. You can install a package that will give you a library of functions that other people have created, and you can create your own functions. Actually, you know what? I'm going to back up for a second. I failed to remember to describe, once you've decided that, hey, I want to do something with, say, the circstats package, how do I learn how to use it? Well, you download it, install it, and once you've run this piece of code that adds it to the library of functions in the current session, most packages, if they were developed properly, you can just put question mark circ stats. So you put the name of the package that you want to learn about and a question mark at the beginning. Circstats not one of them. So Circstats wasn't great in defining, but oh, I wonder if I click this in the packages. Ha! All right, so I'm going to expand this a bit. So I guess, yeah, that's the best way to go see what a package is about once you've installed it and loaded it. You can click it in the packages section, and you can get at least an index. Sometimes there's a nice description for it, but other times you at least get an index of all the functions that are made available by adding that package to the library of functions in your workspace. So now that I've added it, I know that I've got the function circmean, for example. So this says returns the mean direction of a vector of circular data. So again, if I had circular data, I could get the mean of that data by doing circmean. There's circular regression sort of thing. So by looking through the index and the little descriptions, you can get a sense as to what all the different functions the package provides. All right, so that's on contributed packages and functions that you can get from contributed packages. The third class of functions is making your own functions. So the general idea is that whenever you find yourself writing the same thing over and over in your code, it's probably going to be faster to create your own function that achieves that same thing, and then all you have to do is have a short name for your function, and it will be less typing for you. It also can help you make your code more readable to others. So to make your own function, let's say I want to have a function that takes an argument called x and takes whatever value the user provides for x, multiplies it by 5, and returns the result. So to do that, you create a new object. I'm going to arbitrarily name that object my function. I could name it anything, but just happen to like the word my function. And creating that object, it's going to be empty, but inside of it, I'm then going to put the results of this whole thing. So I call the function. The function expects you to put something in between parentheses. You can actually have nothing in between the parentheses. I could have it just like this. So if I want a function to run and not have any customization features to it, I would just have something like that. But I want to be able to customize the function. I want to be able to provide different input and get different output from the function. So you list all the arguments that you want to be able to pass to your function in between the two parentheses. And then you have the squiggly braces. So the squiggly braces encapsulate a series of lines of code that will be run one after the other. And at the end of the function, you should always have a call to the return function. The return function simply tells R that whatever you put inside the return is the value that this function, when it runs, should return to the user. So what I'm doing here is I'm creating a function called my function. It has a named argument called x. X doesn't have a default value. And inside the function, it's going to create this thing called toReturn. And in that thing, in this new object, it's going to put the result of x times 5, whatever x is at that time. And then it's just going to return the value that was computed on this line. So if we run that, nothing happens. Why? Because all we've done is we've defined a function. We haven't tried to use the function yet. So, So using the function, I think the way this is being saved is the last time I ran this workshop, I changed things slightly. So if I wanted to use this function, I'd say my function x equals, let's say, 5. So in theory, because we can see it's a very simple function, what should happen is that x is, I've assigned the value of 5 to x for the purpose of this function. Actually, what I'm going to do, I'm going to clear my workspace. I'm going to rerun this defining of the function so you can see that the function gets loaded as a function. And now what I'm going to do is I'm going to run the function. When the function runs, it's going to create another temporary little workspace. We won't ever see it, but in that temporary workspace, it's going to create an object called x and put in x as its value, the value 5. And then it's going to create another object called toReturn and put as its value the result of x times 5. So it will have to have looked up what x is in its little workspace, see that it's 5, and then put the result of 5 times 5 into toReturn. And then it will return the value of whatever's in toReturn as the value of the function. And at the end, it will just erase the little workspace. So if I run that, we get the value of 25. But notice in our workspace, x doesn't exist. So having assigned 5 as the value of x inside the call to the function doesn't create a variable. So x doesn't persist outside the running of this function. Similarly, toReturn doesn't exist outside the creation of this function. So that's what I mean by a function has its own workspace where you can create objects and things, but the only thing that persists after that function is done running all its commands is whatever you provide as the value inside the inside the return argument function. So just to demonstrate, I can say print x isn't there. Print toReturn is not there. Let's see. All these names that I named things inside the function are completely arbitrary. So the name of the function is completely arbitrary. Could have been anything. The name of the arguments inside the function, again, completely arbitrary. Could be anything. This word or this phrase toReturn could have been anything. So example 2 shows you that. So I'm going to say I'll create a function called hello, arbitrarily named. It takes quirk as the name of its first argument. Quirk gets multiplied by 5 and assigned as the value of a new thing called quark, and we return quark as the result of running that function. So if I say hello 5, let's make it 6 this time, we get, as expected, 6 times 25. Sorry, 6 times 5, which is 30. So the names of things don't matter whatsoever. The fact that I called this toReturn doesn't actually mean that R has any knowledge that it's going to be the value that's toReturned. I name things like that to make it so that when I'm reading my own code as a human, I can see my own intentions, and it makes things a little bit more human readable. But the names of things don't mean anything to the computer. In theory, so in the function definitions here, you always had a function with parentheses, maybe something inside, and then the squiggly braces. You don't actually have to have the squiggly braces. The squiggly braces allow you to put multiple lines, but if you only have a function that's really simple, you can actually just put it all on one line without squiggly braces. So that's example 3 here. If I want to define a function where I just say x times 5, and I guess another feature of this example that it demonstrates is that you don't technically have to use the return function. The function will always return whatever you did last. However, I like using return function because it's a way of being very explicit that yes, I as the human coder intended this to be the value that's being returned instead of, oh, I just happened to delete a line and now the next line is the thing being returned. So I find that most functions you're going to want to have multiple lines, so you're usually going to want to have squiggly braces, and most functions you are going to want to return things, and it's a good idea to always use the explicit return function to do so. Now, example 4 creates a function that, again, we're just going to reuse this name, my function. So if my function's already in memory, it's going to be erased, and a new function is going to be created that has that name. And this time, though, I'm not providing any arguments to function. Or to the function. So it starts off and it's going to say x equals this other thing. So x times 5, to return equals x, return to return. So if I just run this function, I'm just going to say, right, yes, that's what this example is doing. If I just run this function, it's going to start. It's going to look for an object called x. But it's not going to find an object called x because I didn't have any x's in my overall workspace, and I didn't pass it an x, a value for something called x, in the arguments to the function. So x doesn't exist in either its little workspace or the overall big workspace. So it's just going to fail with an error. However, if I create an object called x in the overall workspace, the function will work. So I can run the function. It will look in its little workspace, not find an x, but then it will look in the overall workspace, and it will find an x because we just assigned x the value of 5. So having found that value for x in the overall workspace, it will use it, and specifically, it will copy that value to its workspace, and then it will try to run through the code. Now, this example also demonstrates that what happens in the function stays in the function. So if you try to redefine what x is, so we know that it's found out about x by looking in the global or in the overall workspace, but it's now trying to modify what x is. Those modifications only apply within the functions. They don't modify the value of x that exists outside the function. So despite the fact that we've said x equals x times 5, which if x outside the function was 5, means that inside the function x becomes 25, which is exactly what's being returned here. If I now say print x, it's still 5 because that's what it was before the function. The function doesn't modify x, it just makes a copy of x that it modifies within its own little workspace. So in sort of technical computing terms, that idea is called the scope of operations. There's a global scope, the overall workspace, and then there's a local scope, a little workspace for the function itself. Things that happen in the local scope don't affect things that exist in the global scope. And that's the end of functions. I think I'm going to cut off there because the next session starts off with sort of a new theme, a new topic. We're going to be talking about reading in data. And reading in data is going to be basically the part that, at least at first in your experiences with R, will take you the most time. Once you get your data into a proper format, it's going to be very easy to use R to do actual analysis and visualization. Reading in data is going to be the biggest part. Visualization is probably the second biggest. Analysis is going to be very easy. So yeah, I guess we'll break for lunch. Thanks.